Welcome to this video. Having already made 2 videos presenting my translations into English of the definitions, axioms and propositions of this article, this video will go into a bit more detail with the theory. I will also from time to time touch on some of Lesniewski's more general views to show how the theory of this article reflects these views. This video, however, will by no means be a complete and comprehensive treatment of the contents of this article or of Lesniewski's philosophical, logical and mathematical views. At the time of making this video, there is still much depth and nuance to Lesniewski's work that I've yet to figure out and to discover. Much of the content of this article formed the basis of what Lesniewski would later call mereology, the theory of the relationship of part to whole, which was more fully expounded in his series of articles titled, in English, On the Foundations of Mathematics. I'm currently working on a translation of this series of articles and will hopefully be making some videos covering the contents of these articles in the not too distant future. All of the translations into English of the contents of this article are my own translations unless otherwise stated. I do not claim to be a professional translator, and I don't have professional level translation skills, nor do I claim fluency or mastery of any kind in the Polish language, so if anyone sees any errors or inaccuracies in my translations, then I'd be very grateful if you would let me know. There's relatively little literature on Lesniewski's work. However, a book that I've managed to obtain, and which I'll make several references to in this video, is the book titled The Logical Systems of Lesniewski by Eugene Luskay. This book is not the easiest book to follow, and it helps if you have some familiarity with some of Lesniewski's work beforehand. So I wouldn't normally recommend a book such as Luskay's as an introductory book, but unfortunately there isn't much else on offer. In the short introduction to this article, Lesniewski indicates that he believes that, in comparison to the theories of sets and aggregates which were current at the time of writing, his system has the advantage of eliminating the antinomies of the General Theory of Aggregates, such as Russell's antinomy, while simultaneously not narrowing the original Cantorian notion of aggregates. He also notes that his system does not distinguish between an object and the class which has only that object as a single element. In his 1883 article, Cantor said that, by a manifold or aggregate, I understand generally any multiplicity which can be thought of as one, that is to say, any totality of definite elements which can be bound up into a whole by means of a law. The above translation of Cantor into English is from Philip Jourdain's introduction to the book titled Contributions to the Founding of the Theory of Transfinite Numbers, which contains translations into English of George Cantor's 1895 and 1897 articles on the theory of aggregates. Cantor's definition of aggregate, according to his 1895 article, is as follows. The translation is again from the previously mentioned book. By an aggregate, we are to understand any collection into a whole, M, of definite and separate objects, M, of our intuition or our thought. These objects are called the elements of M. Of course, whether Lesniewski's conception of aggregate is a true and faithful representation of the Cantorian notion of an aggregate will, to a certain extent, be somewhat subjective. I will not make a definitive decision one way or the other, and will leave it to the viewer to make up their own mind. I will come back to Lesniewski's conception of aggregate later in the video. Lesniewski admits that the axioms of his system are true by virtue of the fact that he believes them to be true. The psychological source of his axioms is his intuition. There is no logical source for his axioms, that is, his axioms cannot be proved in his system. Which comes as no surprise, since axioms are typically not provable within any axiomatic system for which they are axioms. There will be a large focus on the mid-sections of this article, that is, the definitions, propositions, etc., from sections 4 to section 9. I won't necessarily go through the work strictly section by section and proposition by proposition, although I will be making some comments on most, though possibly not all, of the other sections. These comments may sometimes be quite brief. Many of the propositions from these other sections are usually quite self-explanatory anyway. The propositions from section 4 to section 9 deserve a bit more attention. The translations of all of the axioms, definitions, propositions, etc. can be seen in the 2 of my earlier videos on this work by Lesniewski. I will include links to these videos in the description box for this video. This work of Lesniewski in the original Polish is in the public domain, and a digital copy can be downloaded freely from the internet. I will include a link in the description box for the website where a digital copy can be downloaded. When we speak of an object, we're referring to a very general type of thing. It's not to be understood that our objects are strictly spatial objects, though of course, spatial objects are included in the notion of object. Indeed, the objects may have a temporal aspect to them. An object may be some kind of event which unfolds over a certain period of time, and the objects are not necessarily connected in either space or time. An object may be known by different names, but a proper name refers to one and only one object. A proper name cannot be assigned to an object that doesn't exist. In contrast to a description doesn't necessarily guarantee that there is an object which satisfies the description, and thus a description may not refer to anything that exists. A proper name, however, always guarantees the existence of an object. This article is mostly concerned with describing the various relationships that exist between different objects, and thus the word object will be replaced with more specific words such as part, ingredient, aggregate, etc., when certain relations between objects need to be emphasized. However, the word object itself is not necessary in this article. Anything that has a proper name is an object, therefore there is a kind of logical redundancy in the expression the object P, which could, in principle, be replaced simply with P, since P must be an object simply by virtue of the fact that we have a proper name for it. The insertion of the word object just seems to make the language a bit more natural. Therefore, part is the only undefined term which is a genuine term of Lesniewski's system, as presented in this article and as is stated in the introduction. Axiom 1 shows that part is not a symmetric relation, and Axiom 2 shows that part is a transitive relation. Proposition 1, however, shows that part is not a reflexive relation. The notion of part could possibly be described as proper part, since Proposition 1 excludes the possibility that a part of an object can be the object itself. Note that an object may or may not have parts. Any propositions which follow and which concern parts of an object are conditional on the assumption that a part of an object actually exists. Some objects may have infinite divisibility and others may not, depending on the nature of the object. However, no special name is given to objects that have no parts. Ingredients are, like parts, objects, though they are objects which have a certain relationship to certain other objects. The existence of ingredients are guaranteed by the existence of objects. As already noted, though, the existence of parts cannot be guaranteed. However, the assumption that an object exists which is a part implies that there is a second object that the part must be a part of, and this second object must be a distinct object from the first object. Proposition 2 shows that ingredients is a reflexive relation. It's quite easy to see that ingredients is not in general a symmetric relation. Ingredients, and of course therefore parts of an object, need not be distinct objects. There may be significant overlap, let's say, between the ingredients. Section 3 gives some of the structure of objects in relation to their ingredients, and Proposition 4 shows that ingredients is a transitive relation. Some of the propositions of Section 3 are quite similar. Despite their similarity, it will be seen that these propositions are necessary in the proofs of later propositions, sometimes for quite technical reasons, in order to show that some object satisfies the conditions of a certain definition. For example, it may seem fairly trivial that, as in Proposition 5, if I is an ingredient of the object P, then some ingredient of I is an ingredient of P, since obviously I itself can always be the ingredient of I that is taken. But nevertheless, full proofs are given of these propositions, and Proposition 5 is used in the proof of Proposition 10. These seemingly trivial propositions, therefore, ensure that the proofs of the propositions remain logically very tight. Definition 2 does not suggest that every ingredient of I, which is an ingredient of P, must overlap with one and only one M. I use the word overlap in a very informal sense here. However, there must be at least one ingredient of I which is entirely an ingredient of one and only one M. Other ingredients of I may overlap with more than one M, or possibly no M's. The M's of definition 2 are ingredients of the object P, which is an aggregate of M's. It would seem, though, that the possibility of I having an ingredient that is not an ingredient of any M would be excluded, since any ingredient of I, say J, would itself be an ingredient of P by Proposition 4, and therefore J has an ingredient K, which is an ingredient of one and only one M, and therefore J must overlap with at least one M. Therefore the possibility of I having ingredients which overlap with no M's is not possible under the assumptions of definition 2. Of course, we're still left with the possibility that ingredients of I, in some cases, overlap with more than one M. Definition 2 in this way ensures that there is no dead space in P that is not accounted for by any M. For definition 3, the original Polish doesn't make it easy to determine whether we're to understand the phrase mnogość wszystkich przedmiotów M as a or the aggregate of all M's. though it is suggested that we're to consider the possibility of more than one such aggregate of all m's. Axiom 4 then ensures uniqueness of this aggregate of all m's. This is quite a common thing with Lesniewski's definitions. Although some of the concepts defined naturally make you think of any object satisfying the definition as being unique, I feel that it's appropriate in the first instance to assume that there may be more than one object satisfying the definition until either an axiom is stated which ensures uniqueness, as in the case of Axiom 4, or until a proposition is proved which ensures uniqueness. Once again, this keeps the logic very tight and avoids, as much as possible, any spurious assumptions working their way into the proofs. Axiom 3 says every object can be considered as an ingredient of some class. That is, there are no objects which cannot be an ingredient of any class at all, and Axiom 4 suggests that there is a unique class of m's. Proposition 8 shows that every object can be considered a class and hence, by Proposition 7, an aggregate. Thus there are no objects that cannot be considered in one way or another as a class or as an aggregate. Note that in Proposition 9, an object P can only be considered as the class of its parts if it actually has at least one part. If the object does not have parts, then it cannot be considered as the class of its parts. Proposition 9 also seems to show that if the existence of a part is assumed, then this automatically implies the existence of a second part. This is related to the results of section 15. Proposition 10 shows that an object is identical to the class of all those objects which are identified as P's. Since P is a proper name for a unique object, then there is, in fact, only one object which is identified as a P. Indeed, we can refer to the P as opposed to a P. A question which may arise as a result of propositions 8 to 10 is that, since P can be considered as the class of ingredients of P, the class of parts of P, provided that P has parts, or the class of P's, are we to consider P in each case as a different class? This question is addressed with the results of section 6, and which I will touch on in the next section of the video. From section 6 onwards, we will see with greater clarity the extent to which Lesniewski's notion of an aggregate differs from the modern concept of a set. It's very important to bear this distinction in mind, since some of the results of this work will seem very peculiar when thought of with the modern widely accepted notion of set in mind. Definition 4 gives a name to the relationship that the m's of definition 3 have to the object P, which is the class of m's, whereas definition 3 gives a name to the relationship that the P, which is the class of m's, has to each of the m's. The P1 of definition 4 is described simply as an element of P. It would seem then that the type of object, the X, that P1 is, isn't important. There may be many possible meanings that can be given to X, and thus P can be considered an aggregate of X's for different meanings of X. Though whichever meaning is applied to X, P is always considered as the same object and the same class, even though it may be considered as a class of X's for different X's. In the diagram, P can be considered as a class of X's, a class of Y's, Z's, W's, U's, and so on. P1, P2, P3, and so on are the elements of P which are X's. P1 primed, P2 primed, P3 primed, and so on are the elements of P which are Y's, and so on. Therefore, the elements of P are P1, P2, P3, P1 primed, P2 primed, P3 primed, P1 double primed, P2 double primed, P3 double primed, and so on. When we say that an object is an element of P, we never need to specify whether the element is an X, or a Y, or a Z, or so on. The example 1 after definition 4 suggests that the elements of an object may overlap. For example, the interval AC and the interval AB of the example overlap. We see from propositions 11 and 12 that the elements of an aggregate are its ingredients. Therefore, element and ingredient are effectively synonymous terms. It's just that some particular collections of ingredients may be known by some other description, such as horse or mouse. We also have, therefore, that all but one element of an object is a part of the object. The only element which is not a part is the object itself. Proposition 14 shows that element of is a reflexive relation, and Proposition 15 shows that element of is a transitive relation. Compare Proposition 15 with modern set theory. For example, if we have an object which is a family F of sets, in other words a set of sets, where set is understood in the conventional modern sense, then an element from one of these sets in F will not in general be itself one of the sets of F. Therefore, element of is not a transitive relation in modern set theory. From what I can understand, the notion of set in modern mathematics and logic is what may be described as the distributive concept of a set or aggregate. On the other hand, Lesniewski's notion of set is described as the collective conception of a set. The details of how collective sets or aggregates behave will become clearer as we progress through the sections. The distinction between distributive and collective conceptions of sets is possibly one of the most challenging issues to deal with initially, especially when the notions of contemporary set theory are quite deeply ingrained and habitual. This is further complicated by the fact that similar terminology is used, such as element but understood in a different sense and with vastly different implications. The following very rough example might help to clarify the distinction to a certain extent. In Lesniewski's formulation of a class or aggregate, suppose we have the object P, which is the class of all bunches of bananas on sale in a certain fruit shop. Then P is also the class of all individual bananas. P is also the class of all parts of the bananas, or even all arbitrary collections of parts of the bananas. Not only are the bananas elements of P, but any pair of bananas would be an element of P. The banana skins would be elements of P. Any part of any one of the bananas would be an element of P, and of course, the whole collection of bananas would be an element of P. With the modern conception of a set, if A is the set of all bunches of bananas on sale in the fruit shop, then this would be a different set to the set B of all individual bananas, which in turn is different to the set C of all parts of the bananas, and which is, again, different to the set of all arbitrary sets of parts of the bananas. A is the set of all bunches of bananas, and so the elements of the set are the individual bunches. The individual bananas are not elements of A. The banana skins are also not elements of A, and so on. Sections 7 and 8 really show how different the two conceptions of set are. Some propositions which, in my opinion, really emphasize the distinctions between the two different conceptions of set are, but not limited to, propositions 14, 15, 20, and 22. The result of proposition 25 may initially be quite surprising. This result really emphasizes another major distinction between aggregate, class or set in the Lesniewskian sense, and class or set in the modern idiom. In modern set theory, sets are not usually permitted to be elements of themselves, since this leads to Russell's famous paradox of the set of sets which are not elements of themselves. Lesniewski's formulation of class avoids this paradox, since Lesniewski's formulation does not distinguish between an object and the totality, or class, whose only element is that object. Lesniewski, as mentioned in his introduction to this article, considers such a distinction to be in conflict with intuition. Page 30 of Leśniewski discusses the illegitimate distinction between an object and the totality of itself. It reads, having pointed out the fallacy in Frege's argument for the necessity of distinguishing between an individual and the corresponding unit set or singular class, Lesniewski did not require an unintuitive distinction between an individual and the totality, i.e. collective class, of itself, the totality of individuals identical with itself, any totality of which that individual is sole ingredient elements, or the distributive class of individuals identical with itself. Proposition 26 forbids any kind of object which may lead to Russell's paradox. Again from Leśniewski, we have the following. For since any individual is the collective class of itself, and is an ingredient element of itself, no individual is a collective class of individuals that is not an element of itself, nor a fortiori, a collective class of such collective classes. So it is simply false, but meaningful to say, that the Russellian collective class is anything at all, even itself, or an element of itself. I've quite a few comments to make on proposition 27. It seems that this proposition is an example of where Lesniewski may have let his guard down a bit when writing this work. The proposition as presented in the current work reads as follows. The statement, if P is an element of an aggregate of M's, then P is an M, is false. Upon a first reading, this is a very unusual proposition because, well, it appears to be false. I personally spent quite a significant amount of time trying to understand this proposition as it's presented here. The reason that I had so much trouble with it is because if M's are interpreted as being P's, then the aggregate of M's mentioned in the statement becomes an aggregate of P's. Then in fact this is, since there is only a single P, the class of P's. Moreover, since P is an element of the class of P's, then P is an M. After much thought, the only way that I could justify proposition 27 was if Lesniewski meant to say something like, it cannot be said in general that if P is an element of an aggregate of M's, then P is an M, which still leaves the possibility that P may sometimes be an M. What suggested to me that Lesniewski meant something more like this latter interpretation is that, in the proof of proposition 27, Lesniewski considers a very specific case which leads to a contradiction. The proof therefore shows that the statement, if P is an element of an aggregate of M's, then P is an M, is indeed false in this particular case, but certainly doesn't suggest that it's always false, merely that it's sometimes false. Well, it turns out that after reading some of Lesniewski's later work on the foundations of mathematics, there's a little note in Chapter 4 concerning this proposition, the translation of which is shown on the screen now, and which acknowledges that there is in fact a problem with the statements of Proposition 27 in the present work, and I think it's more or less the problem which I'd identified. Lesniewski restates Proposition 27 in Chapter 4 of On the Foundations of Mathematics to read, if P is a part of Q, then not, for every R and A, if R is an element of some set of A's, then R is an A, which doesn't suggest that R is never an A, but simply that we cannot count on R being an A. The condition that, if P is a part of Q, is to account for the pathological case where the universe of objects, which is defined in section 12, consists of only a single object Q. Since Q is the only object in the universe, then it clearly cannot have parts. In this case, and without the condition, if P is a part of Q, then the statement, for every R and A, if R is an element of some set of A's, then R is an A, would always be true, since Q would be the only object, and Q would be the same object as the class of Q's, and the only element of the class of Q's would be Q itself. As mentioned in an earlier section of this video, the existence of parts is not guaranteed, and nor is the existence of more than one object. Proposition 27, at least in its modified form therefore, ties in with what was said in the earlier section of the video, where a comparison was made between Lesniewski's conception of a set, class or aggregate, and the modern notion of a set. There is, it seems, a slight error in the proof of Proposition 27 in the current work, which I'll just mention even though it may seem irrelevant in light of the preceding comments. The line after statement 6, it seems that where it says Proposition 3 and 10 should read Propositions 3 and 11. It would also seem that both Propositions 3 and 11 could be simply replaced with Proposition 13. Proposition 10 shows that an object P is the same as the totality whose only element is P. This suggests that there cannot be an empty class, that is, a class with no elements, since where there is no object, then there can be no totality to speak of. Proposition 17 excludes the possibility of an empty aggregate. The statement of this proposition is, if P is an aggregate of M's, there must be some object which is an M. In Chapter 2 of Lesniewski's On the Foundations of Mathematics, we have the problem of the empty class. However, I treated the concept of empty class from the very first encounter as a mythological concept, assuming without any hesitation the position that, if some object is the class of A's, then some object is an A. Even though this quote is from a work of Lesniewski's which appeared in print over a decade after the current work, it suggests that Lesniewski had never entertained the idea of a null class from the outset, including at the time of writing the current article. From a purely formalist perspective, there would be little problem introducing a symbol to represent the empty class, with little or no regard given to its meaning, or whether such a thing existed or corresponded to anything. Lesniewski was critical of this thinking, though. He didn't agree with the idea of simply introducing a symbol which can be manipulated according to a certain set of rules, but simply because the symbol is convenient and makes things work. Lesniewski was from a more philosophical background, and so the meanings and interpretations of his systems are important considerations. Lesniewski doesn't simply create formal systems. Though he did formalize his systems, he didn't do this with the intention of stripping them of their meaning, but simply to make his systems more precise. From Luskay we have that Chwistek asserted that Lesniewski spoke as if it were a common mistake to employ null classes. On a purely formal level, having a symbol to represent a null class is not a problem and in fact is quite useful in many cases. However, when the meaning of the null class is considered, then it becomes more difficult to justify, especially when Lesniewski's collective view of aggregates is taken into consideration. Since an object is identified with the totality which has the object as its only element, then the null class cannot exist because there would be no object in the totality that would be the null class. Luskay's book reads, Lesniewski was never satisfied with ingenious devices or expedients just because they somehow seemed to work, and smoothly duplicated formulas of familiar or desirable shapes. So he voluntarily renounced his right to manipulate formulas arbitrarily and assert nonsense at will, and restricted his creative freedom to posit, postulate, assume, generate, or determine arbitrary and even infinite classes by arbitrary conditions, intuitively meaningful or not. And also we have, But Lesniewski did not agree that in general, our choice of system of symbolic logic is arbitrary, nor consider his a formal system divorced from intuition, an artificial representation whose advantages outweigh its obvious artificiality. The rest of the work introduces the concepts of subaggregate, proper subaggregate, universe, external objects, and complements. None of these concepts presents any real difficulties when Lesniewski's conception of class is sufficiently well understood. Nor do the propositions present any difficulties. Therefore, in order to keep the video to a reasonable length, I'll skip over these latter parts. I'll just finish this video by commenting that Lesniewski apparently intended there to be additional parts to this work. This is suggested in the title of the work, which, in English, is The Foundations of the General Theory of Aggregates.I. The contents of this article were slightly revised and expanded upon, and published in Lesniewski's series of articles published over a decade after the current work, under the title On the Foundations of Mathematics. I'll hopefully be making some videos on this series of articles somewhere along the line. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.